Okay, in this lecture we're going to discuss the first part of our section 1.3 material on polar coordinates. So within this section we're going to describe a coordinate system which was introduced by Newton, which is called the polar coordinate system. And it gives us another way to represent points in the plane that's different from the rectangular or Cartesian coordinate system. So the coordinate system that we're used to working with is that Cartesian system, or sometimes called rectangular coordinates, where every point in the plane is assigned a value x and y. X is sort of a signed distance in a horizontal direction, and y is a signed distance that we move in the vertical direction. But this alternative system, which was introduced by Newton, has some nice applications, which we'll see a little bit later in the semester. It's going to make some of our work much easier. So let's start by introducing some terminology and see how exactly points in the plane will be defined. So we start by choosing a point in the plane, which will be referred to as the pole, or we could think of this as the origin, and labeled as capital O for origin. So let's keep track of what we're doing in our figure below here. So I'm going to start by choosing some central point, which I'll refer to as the origin or the pole. And then if P is any other point in the plane, so let's choose some other point within the plane, call it P. We're going to define R as the distance from the origin to that point P. So if we were to connect the origin directly to this pole, or to this point P, the distance along that line segment is what we call R. Now, we would sometimes call R the radial coordinate, so a little extra terminology here. R is sometimes called the radial coordinate. And then we would let theta be the angle measured in radians, which lies between the positive x-axis and the line connecting OP. That is the line from the pole to our point P. So illustrating here, we would have the positive x-axis, which in polar coordinates is sometimes called the polar axis, and theta is the angle measure in radians from that polar axis, or the positive x-axis, to the line from O to P. So this point, P, can be represented as an ordered pair, R theta, where R and theta are called the polar coordinates of that point P. So as I mentioned, R is called the radial coordinate, theta is sometimes called the angular coordinate. So this polar coordinate system that we've described here gives us a way to represent all points in the plane. Instead of in terms of x and y, we can define any point in terms of r and theta. That is the distance from the origin directly to our point along some line is the value r, and theta is the angle measure from the positive x-axis, or sometimes called the polar axis, to the line which connects my point to the origin. Now, something to note here, we will use the convention for the polar coordinate system that the angle is positive if we're measuring in the counterclockwise direction from the positive x-axis. So if I'm rotating from my polar axis counterclockwise, this would be a positive value of theta, and we would assign a negative value to theta if we're rotating in the clockwise direction. So let's say that we had some other point, let's call this P. We look at the line segment from O to P, and whatever that distance R would be, whatever that distance is, we call R, which would be the radial coordinate of that point. And the angle, theta in this case, would be negative since we're rotating in a clockwise direction from that polar axis. All right. Now, one other thing to mention here, so I'm going to say moreover, we can extend the definition of polar coordinates, r theta, to the case where r is negative by taking the convention that if we have a point given as negative r theta, we would say that that is the same point as r theta plus pi. So to illustrate that convention here, let's think about how this might work. So in our right-hand figure, we have the pole or the origin O. We have our positive x-axis, also referred to as the polar axis. And let's say that we have some point P, which has coordinates negative r theta. So how exactly could we think about that point if r is negative? Well, there's a couple of ways to think about it. One way is to consider that the same point as positive r theta plus pi. So if we were to rotate by an angle of theta, we have this, let me use the same color here, this line segment that moves from the origin to some point P. So we rotate by that angle measure theta, and then if r is negative, one way to think about this point is we move backwards from that line segment a distance of r units to get to our point, if r is negative. Or an alternative way to define this would be once we've rotated by theta, we could move in the positive direction of that line by r units. But since r was supposed to be negative here, we would then change our angular coordinate to be, instead of theta, theta plus pi. So from here, we would then change theta to be theta plus pi. So we rotate an additional pi radians or 180 degrees, in which case then r would be positive, and we can see that we get the same point as negative r theta. So a couple of ways to think about that case where we have a negative radial coordinate. So let's look at some examples to familiarize ourselves with this polar coordinate system. So in this first example, we are asked to plot the points whose polar coordinates are given. And then we're supposed to also find two other pairs of polar coordinates at that point. One which has a positive value of r, and one which has a negative value of r. So in part A, we have the point given in polar coordinates as 1, 5 pi over 4. So these coordinates are r and theta. So let's start by plotting this point. So we have, let's say we have the standard xy plane that we might consider. So in order to represent this point in the plane, we would assign our origin O, and our radial coordinate was 1, and our angular coordinate was 5 pi over 4. So this is defining a point where from the polar axis, or positive x-axis, we rotate 5 pi over 4 radians in the counterclockwise direction, since we had a positive value of theta. And then along the line formed by that angle, we move 1 unit outward from the origin. So from the origin, we move out along that angle, or the line defined by that angle, a distance of 1 unit. So this would be our point P, whose coordinates are 1, 5 pi over 4. Okay. Now, we're also supposed to find 2 other pairs of polar coordinates to represent this point. One which has a positive r value and one which has a negative r value. So let's discuss how we could do that. Now, another way to get a, let me maybe squeeze this in, give myself a little more room. Another way to get a polar coordinate that represents the same point with a positive r value would be to use the same value for r that I'm given here, 1, and for my angular coordinate, which was 5 pi over 4, I could either add or subtract 2 pi or any multiple of 2 pi. Well, that is any integer multiple of 2 pi. Now let's think about why that's true. If I add 2 pi or subtract 2 pi from that angle, let's think about what that does. So at an angle of 5 pi over 4, I was at this line segment. So if I just add 2 pi to that, that means I'm just going to make 1 extra revolution about this circle and then still move 1 unit outward. So I would be defining the same point, but by using a different angular coordinate. So this would be 1, and then let's see, we've got 5 pi over 4 plus 2 pi would be 8 pi over 4. So we could say 1 and 13 pi over 4. That would be another representation of this same point. Now, if we want a representation in polar coordinates where r is negative, well, we could change the value of r to a -1, and by making that change, I would have to take the angle that I was given, 5 pi over 4, and either add or subtract pi to that value, so that I would rotate by another 180 degrees. So an equivalent representation would be as -1, and then 5 pi over 4 plus pi, or I could take 5 pi over 4 minus pi, doesn't matter. So if I subtract pi, I would have pi over 4 with a -1. So let's think about why that represents the same point. Well, let me erase some of my work here. So if our angle measure is pi over 4, that is 45 degrees, I would move outward in this direction, and I would be looking at a line segment extending in that direction. But if r is -1, I would be moving backwards from that line segment 1 unit. And that would, of course, define this same point P. Alternatively, we could have subtracted pi from that original angle measure, and I would have the exact same expression. So here we have 2 different polar representations of that same point aside from the one that we're given. So something that we can note from part A of this example is that the polar representation of a point is not unique. So every point in the plane has an infinite number of representations in terms of polar coordinates. However, each point in the plane has only one representation in terms of rectangular coordinates. So why do we have infinitely many representations in terms of polar coordinates? Well, we mentioned for any point whose polar coordinates are known, we could add or subtract any integer multiple of 2 pi to that angular coordinate, and we would get the same point. We would just maybe wrap around this circle multiple times by adding more and more multiples of 2 pi. So there's infinitely many representations possible. So let's look at some other examples. In part B, we have the point given as r theta is equal to 2 negative 5 pi over 6. So let's plot that point first. So here, drawing on top of our standard xy plane, we have our origin O. We would rotate by negative 5 pi over 6. So the fact here that theta is negative means that we are rotating 5 pi over 6 radians, but in the clockwise direction. So rotating 5 pi over 6 radians in the clockwise direction, we have a line defined by that angle, and our radial coordinate r was 2, which means along that line we're moving a total distance of 2 units outward. So this would be our point P, whose coordinates are 2 negative 5 pi over 6. So we want other representations of that same point, one which has, again, a positive r value and one with a negative r value. So let's think about how to get another representation with a positive r. Let's say r is 2. So I could take the angle that I was given, negative 5 pi over 6, and I can add or subtract any multiple of 2 pi. So if I add 2 pi to my negative 5 pi over 6, to save myself a little room, let me just show what we get. So negative 5 pi over 6 plus 2 pi, which would be 12 pi over 6, is 7 pi over 6. So that would be another valid representation. Instead of rotating clockwise 5 pi over 6 radians, I could express this as a counterclockwise rotation by theta equals 7 pi over 6 radians, and then still move 2 units outward along that line segment. And if I want a negative r value, let's say negative 2, I would take my angle measure and add or subtract pi to that angle measure. So if I took 7 pi over 6 and I subtract pi, I would have 1 pi over 6 with a value of negative 2 to represent that same point. So let's look at part C. In part C, we have the point whose polar coordinates are theta, are negative 3 and 3 pi over 4. So let's start by plotting that point. So a couple of ways we can do it. We see we have a negative r value here. So one way to think about plotting that point is by rotating by the angle measure theta that's given, 3 pi over 4. So we would rotate in the counterclockwise direction since theta is positive by 3 pi over 4 radians, and we would have this line segment from the origin moving outward along that angle measure. But since r is negative 3, we're going to move backwards from that line segment a distance of 3 units. So this would be our point that's given. Now, other ways to represent that same point, well, if we stick with a negative r value, let's say negative 3, I could either add or subtract some multiple of 2 pi to the angle measure that we were given. So maybe if I add 2 pi to 3 pi over 4, I would have 11 pi over 4. And if I wanted to change the r value from a negative to a positive, let's say positive 3, then I would need to add or subtract pi from the angle measure that we're given. So adding pi to 3 pi over 4, I would have 7 pi over 4. So this would give me another way to represent that point. Okay. So in these first examples, we're just illustrating what exactly these r and theta values mean. Specifically, if we have some points with a negative r or negative theta values, we want to see how to plot these points and get alternative representations of a point in polar coordinates where we might want a positive or a negative value for that radial coordinate. So let's look at how to convert a point from one coordinate system to the other. So typically we can represent, or we'll be interested in representing points in the plane either using the Cartesian coordinates x, y, or using these new polar coordinates r, theta. So if we have a representation of a point in one system, we'd like to be able to move to a representation in the other coordinate system. So the following theorem gives us a conversion for points between those two systems. So let's say that we are given a point P in the plane whose Cartesian coordinates are x, y, and whose polar coordinates are r, theta. So we claim that the following conversion formulas will hold true. So if we have r and theta, we can find the xy coordinates by saying that x is equal to r cosine theta, and we can find y by saying y is r sine of theta. Now, conversely, if we're given the Cartesian coordinates, x and y, for some point, we can define the polar coordinate, r, as the square root of the sum of x and y squared. And theta, the angular coordinate, can be found by solving the equation tangent of theta is equal to y over x. So let's think about why these conversion formulas hold, and this will give us a way to remember these conversion formulas. So let's say in the plane, say the xy plane, or however we've assigned a coordinate system, we have a point P. So P here has rectangular coordinates x and y, so how far we've moved in the x and y direction. So of course this forms a 90-degree angle. And we also have a representation in polar coordinates as r, so the distance we've moved from the origin outward to our point is r, and we have an angular coordinate of theta. So of course this is the same point. So what is the conversion formula between these coordinate systems? Well, we can make use of the fact that this triangle which we formed is a right triangle. So we know for instance, that sine of the angle theta, our angular coordinate, is equal to the ratio of the opposite side of my triangle y over its hypotenuse, which is r. And cosine of the angle theta is the ratio of the length of the adjacent side, which was x, and over the hypotenuse, which was r. So multiplying both sides of this equation by r, we have r sine of theta is equal to y, and r cosine of theta is equal to x. So that gives us our first two formulas from that theorem. X is r cosine theta, and y is r sine theta. And now to get the other two formulas, well, the formula for r follows directly from the Pythagorean theorem. Since this is a right triangle, we know that the sum of the squares of the legs of this triangle, that is x squared plus y squared, must equal the hypotenuse squared. So solving for r, we would have the square root of x squared plus y squared. And in order to solve for theta, well, we can make use of the fact that tangent of theta is defined as the ratio of the opposite over the adjacent edges of our triangle, in this case y over x, and then we can solve for theta based off the values of x and y. So we have these conversion formulas which hold between the Cartesian coordinate system and our polar coordinate system. So let's look at some examples where we will convert from one system to the other. So in this first example, we are asked to find the Cartesian coordinates, that is x and y, of the polar point. So the points that were given here are in polar coordinates r, theta, and we want their rectangular coordinates. So here let's take a look at this. In part A, in order to get x, well, x is defined as r times cosine theta, and here r is 4. So we have 4 times cosine of theta, which is 5 pi over 4. So we have 4 times cosine of 5 pi over 4 is negative square root 2 over 2. So multiplying by 4, we have negative 2 times the square root of 2. And to find the y-coordinate, we would take r times sine of theta, which would be 4 times sine of 5 pi over 4, which is 4 times negative root 2 over 2. So we have negative 2 root 2. So for this point given in polar coordinates, the corresponding rectangular coordinates, x, y, would be negative 2 root 2, negative 2 root 2. All right. So let's verify that those two different coordinates would be representing the same point. So a little extra practice with plotting here. So in the xy plane, we're talking about a point whose polar coordinates were given by 4 and 5 pi over 4. So we would start from the positive x-axis and we would rotate in the counterclockwise direction, a value of 5 pi over 4 radians. And then along the line segment defined by that angle, we would be moving outward 4 units. So this would be our point P. Now the corresponding x and y coordinates for that point would be negative 2 root 2 and negative 2 root 2. So that's another representation of that point using those rectangular coordinates. We see that it does seem that those two sets of coordinates are representing the same point P here. So let's look at another one. In part B, we are given the polar point, r theta is equal to 2 pi over 3, and we want the Cartesian coordinates, x and y. So x, again, is given as r times cosine of theta. So here we would have 2 times cosine of pi over 3. So that is 2 times cosine of pi over 3 is 1/2. So 2 times 1/2, we have a value of 1. And y is defined as r sine theta. So here we would have 2 times sine of pi over 3. So that is 2 times sine of pi over 3 is square root of 3 over 2. So we're left with root 3. So the Cartesian coordinates that we're after, xy, would be 1 and root 3. Okay. So again, to get a little idea or to sort of check our work and see that this seems reasonable, let's think about plotting the point using both coordinate systems. So in the plane, we have the point whose polar coordinates are 2 and pi over 3. So we would start by looking at the radial coordinate, or the angular coordinate, theta, which is pi over 3. So I would rotate pi over 3 units in the counterclockwise direction, since theta was positive. And then along the line formed by that angle from the origin, I would move outward a distance of 2 units. So the corresponding xy coordinates would be 1 and the square root of 3. Okay, so it does seem reasonable. We think we've got our solution correct here. Now, in our next example, we'll be looking at a similar problem, but moving in the opposite direction as to what we just looked at. And we see that this conversion can be a little bit trickier. So here we are asked to find the polar coordinates, r theta, of the rectangular point where we're specifying that r needs to be positive. So the points that were given in this example are rectangular or Cartesian points, x, y. So here we have x and y are -8, +8, and we want r and theta. So recall that r is defined as the square root of the sum of x squared and y squared. So here r would be the square root of -8 squared, which is 64, plus +8 squared, which is 64. So we have the square root of 128. Now, of course, this is 2 times 64. Square root of 64 is 8. So we have 8 root 2 for our r value. And to find theta, we use the equation tangent of theta is equal to y over x. So here we would have tangent of theta is y, which was 8 over x, which was -8. So we have tangent of theta is -1. So let's think about the angles for theta such that tangent of that angle would be -1. So since tangent would be negative, that means that x and y have opposite signs. And since tangent of theta, or since it has a magnitude of 1, that means that x and y would have to be the same quantity, maybe just differing in signs. So one option would be the angle 3 pi over 4, or another option would be the angle 7 pi over 4. We know we're either in quadrant 1 or quadrant 2 or quadrant 3. Quadrant 2 or quadrant 4 in order for x and y to have opposite signs. Now, the question is, well, which of these two angles do we want? So for this point, we had a rectangular coordinate, which was given as -8, +8. So that means that we lie in quadrant 2. Since our x value was negative and our y value was positive. So which of these two angle measures lie in quadrant 2? Well, the only one would be 3 pi over 4. The value 7 pi over 4 lies in quadrant 4, which is not where the point that we're given lies. So the point can be represented as r theta equals 8 root 2 and 3 pi over 4. Okay. So we can also see this or verify this by graphing. So in our xy plane, we're looking at the point -8, +8 for our point P. So we could represent this as the point in polar coordinates where theta is 3 pi over 4. So we rotate counterclockwise by 3 pi over 4 radians. And then along the line determined by that angle from the origin, we move outward a distance of 8 root 2 units to get to that point. So another representation that we could use here. All right. So let's look at another one. In part B, we have the rectangular coordinates x, y are 2 root 3, -2. So to find r, we're supposed to be taking the square root of the sum of x and y squared. So here we would have r is the square root of, x was 2 root 3. So squaring it, we would have 4 times 3, or 12, plus -2 squared is +4. So r is then root 16, or 4. Now to find our theta value, we would use the fact that tangent of theta is equal to y over x. So here, tangent of theta would be equal to -2 over 2 root 3, or -1 over root 3. So let's think about the angles, theta, such that tangent of theta is -1 over root 3. So those angles would be a 5 pi over 6, or 11 pi over 6. And the question is, well, which of these angles do we want to represent our point? So to answer that, we have to think about what quadrant our point lies in. So for the given point, we had a positive x and a negative y value, which means that we lie in quadrant 4 of the plane. So which of these two angles gives us a point that lies in the fourth quadrant? Well, our 11 pi over 6 is an angle that lies in that quadrant. So theta will be 11 pi over 6. So for our answer, we would say r theta is the point 4 11 pi over 6. And of course, we can verify that by plotting. So within our xy plane, we could represent this point in terms of polar coordinates by rotating by 11 pi over 6 radians in the counterclockwise direction. And then along the line determined by that angle from the pole or the origin, we would move outward 4 units. And this point could also be represented in terms of rectangular coordinates as x equals 2 root 3 and y would be negative 2. So an alternative representation of that point. All right. So in our last example, part C, we have the point whose rectangular coordinates, x, y, are given as negative 3 and positive 4. So to find r, we're taking the square root of the sum of x and y squared. So we would have r is the square root of negative 3 squared, which is 9, plus 4 squared, which is 16. So we have r is the square root of 25, which would be 5. So to find theta, we use the fact that tangent of theta is equal to y over x. So in this example, tangent of theta is 4 over negative 3, or negative 4/3. And using the unit circle, well, there's no familiar angle theta that would be a multiple of like pi over 2, pi over 6, or pi over 4, for which tangent of theta would be known to be negative 4/3. So in this case, we would have to make use of the arctangent function. So theta, we could take as arctangent of negative 4/3, but we've got to be a little bit careful when we make use of this arctangent function. So something that I want to illustrate in this example is something that's a little tricky when you're using the arctangent function that you want to be careful of. So we're not quite done. We can't just say that theta is equal to this value because this angle may not give us a point in the correct quadrant. So let's think about what quadrant we want to be in. So here the point we're given is negative 3, positive 4, which means that we lie in quadrant 2. But let's think about where this arctangent angle lies. So I claim that this expression, arctangent of negative 4/3, lies within the interval from negative pi over 2 to 0. That is, I claim this angle lies in quadrant 4. Now, why would that be the case? Well, recall that the domain, the range of the arctangent function is restricted. So if we look at the graph of the arctangent function, it has horizontal asymptotes of positive pi over 2 and negative pi over 2. So when I'm talking about the arctangent of some angle, then that angle must, or arctangent of some quantity, that angle that I'm defining must lie between positive and negative pi over 2. So that means that it would lie somewhere in the right half plane. But I want to be in quadrant 2. I want this second quadrant, which I can't get directly from this arctangent value. So how do I know that this angle lies between negative pi over 2 and 0? Well, let's take a look at our graph. We're looking at arctangent of a negative number, negative 4/3. So here the graph I'm looking at is y is arctangent x. So for a negative value, I can see that the value for arctangent would lie somewhere between this lower asymptote of negative pi over 2 and 0. So that means that I would be somewhere within this quadrant 4. So this is my theta equals arctangent of negative 4/3. Now to get to quadrant 2 from here, I would have to take this angle measure that I was given, and I would have to add pi to that angle measure. So I want to get a rotation from that angle by 180 degrees, which would be pi plus arctangent of negative 4/3. And then I would move the same positive distance outward along that line segment by a value of r equals 5 to lie in the correct quadrant. So here, the value of theta that I need to make sure I lie in the correct quadrant would be pi plus arctangent of negative 4/3. So for this one, a little bit tricky when we're making use of that arctangent function because we need to ensure that we are in the correct quadrant. And the downfall of the arctangent function is that its range of values is only from negative to positive pi over 2. So here, the polar coordinates that we want are 5 and pi plus arctangent of negative 4/3. Okay.